Okay, so before we actually go over those problems, let's kind of get into like what the idea behind a hypothesis test really is. So the hypothesis test is used to like test the validity of some claim. So I'm just going to make up an example. So imagine you bought a pack of, I use this example in class, but imagine you bought a pack of Skittles, right? And you opened the bag and let's say there's 20 Skittles in there. And of those 20 Skittles, 10 of them were red. Okay, well, that seems a little high that half of them were red because there's five colors. So you would expect that about 1/5 of the Skittles would be red. So you go, okay, maybe I'm wrong about that assumption. Maybe it's not 1/5 of all Skittles are red. Maybe there's actually a higher percentage of the Skittles are red. So what you could do is you could conduct a test. And let's say you took a sample of, I don't know, 200 bags of Skittles. um, you open them all up and you notice that the average number of Skittles from these 200 bags, if each bag has 20 Skittles, let's say the average you found was, I don't know, 8.2. On average, you found 8.2 red Skittles per bag. When you go, okay, but if they're evenly distributed, I should expect that 1/5 of the Skittles should be red. So I should expect 4 red. I'm getting an average of 8.2. That's pretty high compared to what I would expect if they were evenly packaged in each bag. So then I go, okay, if basically the whole point of the test is if this is true, we assume this is true. If 1/5 of the bag is supposed to be red, how unlikely is it that I get an average of 8.2 red Skittles from 200 bags? And you measure how unlikely that is, and kind of the cutoff is 5%. So if the chances of this happening is less than 5%, or zero point zero 0.05, and it does in fact happen, then we can say that it's so unlikely to happen by chance that it must be happening because of something else. So I opened 200 bags. I noticed that from those 200 bags, the average number of red Skittles that I got per bag was 8.2. The chances of that just randomly happening, if the Skittles are evenly distributed, let's just say I calculate my p-value to be 0.03216. So if the chances of that just randomly occurring, if all of the Skittles are evenly distributed, is 3.2%. So we compare that percentage to 5%, and if it's less than 5%, that means it's really unlikely. So chances are that this occurred not randomly, but because this statement is in fact false. So I could say, okay, I got an average that was so high that I can actually say that I think the average is higher than 4 per bag. And that's the entire basis of the hypothesis test. So I'll kind of restate that when we look at these questions. So they don't really give us any context here, but it just says you wish to test the following claim at a significance level of 5% or 0.05. That's some mean. They're telling us the mean of something is 71.9, and we want to try and prove that it's less than that. So we know the standard deviation, and that's sigma. So that means we can run a z-test. If we didn't know sigma, we'd have to run a t-test. Very similar, just means that we're less confident, so the curve is actually a little bit wider. We plug everything in, so if I go to run the z-test, stat test, z-test, my null mean is 71.9. My null sigma is 19.3. Oh, I don't want to do data. I want to go up and do stats. 71.9, 19.3. My sample mean is 67.3, and I have a sample size of 58. I'm trying to show that my mu alternative is less than the null. So I calculate. So I get my test statistic. 3 decimal places would be negative 1.815, which is perfect. And then my p-value would be 0.0347. So I think you need one more decimal place here. So whatever we're talking about here, the chances that we would get something like this, whoops, that's a horrible circle job. The chances we would get this output, if this null was true, is 3.7%. So then we always compare this p-value to alpha. So if since our p-value is less than 0.5, p is less than alpha, that means that we can reject the null. It's so unlikely that the null hypothesis is probably not true. So we reject the null. You never accept the null. Okay? That's just not an option. So it's either reject the null or fail to reject the null. It's kind of like the court of law, right? You never really say someone is innocent. You just say that they're either guilty or not guilty. We cannot say they're innocent. We can either just prove or not prove guilty. And then you want to kind of state your state your conclusion in terms of the alternative hypothesis. So if we go back to, this was number 2, I believe. So this says the sample data supports the claim that the population mean is less than 71.9. Yeah, you're always going to word your conclusion in terms of the alternative hypothesis. So let's look at another example. So I think this is number 6. Again, no real context here, but there's some mean that equals 76.4. We're trying to show that it's larger than that. The only difference now is they want us to input data. So I'm going to start by going to my stat list. I'm going to hit stat and then enter. And I'm going to enter these 3 data values into L1, just like that. And then I'm just going to run the test like I normally would. We do not know the standard deviation, so this is going to be a t-test. We don't know sigma, so we're going to run a t-test. So we'll go to tests, t-test, and now I'm actually inputting data. So I'm going to click on the data option and then just fill everything in. My mean is 76.4, my null mean. The list of data is in L1. Never change this frequency. This frequency is always going to be 1. And we want to show that our alternative is higher than that. So our test statistic here is going to be 0.0347. The p-value is 0.3808. 0.3808. So remember here they changed it. So now 5% is not even good enough. Our significance level is 1%. So if I compare p to my alpha, p is greater than alpha. So remember, the way you can remember this is if p is less than alpha, we reject the null. If p is low, reject HO. If p is low, reject HO. So if p is high, we fail to reject. P is greater than alpha, so we do not reject the null. It's never accept the null. It's either the top or the bottom. So we fail to reject. So we cannot claim the alternative. So we cannot claim that the mean is higher than 76.4. So let's see here. There is not sufficient evidence to warrant rejection of the claim. No, that's not good. It's not that one. There is sufficient evidence to warrant rejection of the claim that the population mean is greater. No, that's rejecting the alternative. There is not sufficient sample evidence to support the claim that the population mean is greater than 76.4. There you go. So we always write it in terms of the alternative, whether we can show the alternative or we can't show. So if we did get a p-value that was lower and we rejected the null, the answer would be this one. The sample data supports the claim that the population mean is greater. The only other way you can write it is that there's not enough evidence to show that the population mean is greater. So there's your answer there. And that's really all it comes down to, is just calculating your test statistic, your p-value, comparing your p-value to alpha. Usually alpha will be given. If alpha is not given, then it's implied that alpha equals 0.05. Unless it says otherwise, we assume this. Always write your alternative in terms Always write your conclusion in terms of the alternative.